Welcome, everyone. So nice to see people in person again. We're up almost to double digits. Not quite, but we're getting closer every time. Big day today. So today is the due date for assignment 2. And I've been noticing a very sudden increase in the number of submissions for assignment 2, which is great. I took a look at a few of them, but not very many, to be honest. My plan is to start going through those probably next Wednesday, is the way things are looking scheduling-wise right now. In terms of other things, we have, after today's class, 3 classes left. I'm still trying to decide exactly where I want to go next week with our remaining classes. But my plan is to not hold a class on Tuesday. Tuesday next week, yes, but the Tuesday after, which is the 13th, which is the last day of classes, we'll just call it quits next Thursday. We did save a bit of time this year compared to other years for a couple of reasons. One is we didn't have an in-person midterm. That usually takes a whole class. Another thing that usually takes a whole class is the submission of assignment 2. When everyone was here, I used to get a large number of them on memory sticks, and I would devote a whole class to collecting those and copying them off the memory stick and then giving them back right away. Clearly that wasn't really in the cards this year, so it saved us some time as well. So I don't mind taking a bit of time on the other end. All right, let me know if the sound is bad online, although my little sound monitor here appears to be happy at the moment. We're going to do a unit today, and I say start, but we're probably going to finish it. This one's pretty quick. It's a shorter unit than the previous one that we already finished, which was on what? Pesticides? Yeah. There's another unit assignment for this one that's open today. It'll probably close this time next week because 1 week after we finish, which is probably going to be today's class. And I think there's 8 questions from this unit. So I think that puts us up over 100 now. So we're at the promised number, at least. Great, so let's jump in. And this unit, I'm calling it topics in food chemistry as opposed to just food chemistry because, again, this is like a massive field and there's no way we could even hope to like scratch the surface. So I'm not trying to claim at all that I'm going to be complete or comprehensive with our coverage in this unit. There's just a few kind of key things that I thought might be interesting to kind of throw in here and discuss, and hopefully people agree with me. So food chemistry. What we're going to do is talk about, I guess, the different types of chemicals that are in food, and we're going to leave one very important one out, and the one we're leaving out is proteins. And I considered adding a chunk on proteins, but my schedule did not allow that. So we have a discussion on the other 2 main nutrient things that you find in foods, which are carbohydrates and fats. So carbohydrates actually it's got a good name. It's got a name that tells you a little bit about the chemical structure of the compound. So carbohydrate, the actual word, carbo means carbon, hydrate means water. So it's a combination of carbon atoms and water molecules put together to make some compound. So we would say a carbohydrate would have this general formula, CH2O, so carbon plus water, with the N there, meaning there's going to be some number of that unit in the molecule. So if it has that in the structure, we would call it a carbohydrate, and many of the food sources that we eat are carbohydrate based. So anything that we would consider a sugar or a starch are examples of carbohydrates. They are compounds that have that ratio of carbon atoms to water molecules in them. They don't look anything like carbon atoms or water molecules in the final structures, and there's a wide variety of possible carbohydrates. At the very simplest though, at the basic level for carbohydrates, we would say all carbohydrates, actually I got to switch to my slide view here. I'm in big camera mode, thank you. There we go. You don't want to see my face, you want to see my slides. Great, so we have what we call monosaccharides. These are sugars that contain just the smallest basic fundamental carbohydrate unit, which is generally a molecule that has 6 carbons and then 6 waters. So we have, these are very common, what we call monosaccharides: fructose, glucose, and galactose. They have pretty similar structures, except the orientation of a couple of groups is what differentiates glucose and galactose. Fructose, you can see, kind of has a ring with 5 atoms in the ring. You know, if you count them 1, 2, 3, 4, 5. It's based on a pentagon, whereas the other 2 have 6 in the ring. We sometimes call the 5 ring ones pentoses, and the other ones hexoses, because of the number of atoms in the ring. But they're all pretty similar. You can see that they all have the same molecular formula. And because they have the same molecular formula but different structures, we would call these things isomers of each other. Great, simple sugars. We have something we could call maybe a more complex sugar, where we just basically bond together through covalent bonding 2 or sometimes more simple sugars. So a very common one is to put 2 together, which we would call a disaccharide. So 2 monosaccharides put together gives you a disaccharide, and sucrose is a common example. Sucrose is sort of just the normal, ordinary, sometimes called table sugar. This would be the sort of sugar that you would buy in a big bag and, you know, put a cup of in your cooking or baking and stuff like that. So this is just a unit of glucose plus a unit of fructose, so 2 monosaccharides that are coming together. They have a covalent bonded linkage through there, which gives you a molecule of sucrose, which has the structure C12H22O11. So what this really means is that there's 12 carbons plus 11 waters. So in the process of putting 2 simple sugars together, you actually lose a molecule of water. In this process where you lose a molecule of water and put 2 things together, it's a chemical reaction we call condensation, which isn't on the slide. You don't have to know that, but if you cared, that's why. That's where that extra water went. This is a different disaccharide. Instead of using glucose and fructose, which gives you a molecule of sucrose, if you picked instead glucose and galactose, those 2 together give you a different simple sugar, a different, I guess, complex sugar here, which we would call lactose. And lactose is, of course, the sugar that is the major carbohydrate that's found in milk. And lactose is an isomer of sucrose. They have the same molecular formula, but different chemical structures. Fair enough. If you wanted to put more than just 2 sugars together, you can do this too. So if you take glucose and you string together a long chain of glucose, so a long chain of glucose we would call a polymer, right? After our chapter on polymers, we know all about those now, where the monomer would be a unit of glucose. And that monomer repeated again and again and again in a long chain gives you a molecule of starch. And you can see in this example, every starch molecule doesn't have that structure. It's just showing you that there are up to thousands of these individual units in a single chain or molecule of starch. So starch is a very common way that plants will store energy in a physical chemical form, which, you know, potatoes are loaded with starch. Many other starchy foods like flour, corn, foods like this, rice, they can have high amounts of starch in there. which our body then breaks down bit by bit down into the individual glucose units, and those glucose units our body then uses for energy. Converts them into carbon dioxide and water, and we get that energy out. Good. It's actually interesting the way these glucose molecules bind together when you make starch. And I just want to focus on this for a second. You notice how that oxygen bond is pointed down and down, so they're kind of both coming downwards. See if I can get my fingers in the camera. They're both coming downwards towards that oxygen. That's trying to represent a very specific structural way that these two molecules bond to each other. Whereas if you look at it in this molecule, which is cellulose, this one is up. So the carbon to the oxygen is pointing up, and then this one, it's down. So whereas in glucose, it's down, down, this one is up, down, and that difference actually makes cellulose completely unreactive in our cells. We don't have enzymes that can break cellulose apart. We have enzymes that can break starch apart, no problem, but that small structural change makes cellulose extremely resistant to chemical breakdown in our cells, in our body. And what that means is that this basically, if you eat cellulose, these long chains don't get broken down and absorbed. They just travel right through you. And the term we might use for cellulose in our diet would be fiber. So fiber is just a molecule like cellulose that survives intact through your whole GI process, and having a diet that has enough fiber in it is actually very important for health as well. So even though we can't break cellulose down and use it for food, it's important that we get some in our diets. I don't think any mammals are capable of breaking down cellulose. But there are organisms that can. A lot of microorganisms can. And so if you look at cattle, like cattle are fed hay or silage or whatever else, but they can digest hay, which is largely just cellulose. And the way they're able to do that is not because they themselves possess the enzymes to break it down, but they actually harbor certain microorganisms. I'm not sure if it's bacteria or what it is. And they have a very complex digestive system, I believe, with 4 stomachs. And it kind of ferments in the stomachs as it passes along. And so they're not really digesting it. They're getting their host microorganisms to do it for them. I believe the same thing is true with termites. And it's because cellulose is so hard to break down, that's the reason why both termites and cattle give off so much methane. Because methane is a byproduct of the decomposition of cellulose. So really, think about it. If we were able to just instantly evolve, like, you know how people have superpowers, or, I mean, people don't really have superpowers, but people talk about, if you could have any superpower, what superpower would you want? And people are like, yeah, ability to fly and all that kind of thing. A great superpower to have would be the ability to digest cellulose. I mean, it'd be difficult to make a movie out of that, I think. But if we could do that, like you think about a field of corn, and that field of corn, you got a couple little cobs per plant, and you throw out a whole bunch of the stalk and the leaves and all that sort of thing. Same thing with wheat. We take the little seed thing at the top, and we throw out all the rest, which is straw. If we could digest cellulose, we could eat all that stuff too. And then we would need way less farmland, which is pretty good, I guess. Not too exciting, but whatever. It turns out, so we have receptors on our tongue, and our receptors on our tongue are sensitive to sugars and sugar substitutes, as we'll see. And of course, our bodies crave sugar because especially simple sugars are very rapidly broken down in our bodies and very rapidly provide energy. So we've evolved this, I guess, preference for very sweet foods, which for most of our evolutionary process have been relatively not abundant. Like what sweet foods you might find, you might occasionally come across, a beehive and get honey or something like that. But certainly you can't just go to the corner store and get candy like we can now. So it turns out our tongues actually have different sensitivity to different sugars, different sweeteners, depending on what the sugar is. So using this using sucrose as kind of our standard, table sugar as our standard of 100, we can look at the sweetness of a bunch of various other sweeteners that we can find. So honey is one. Honey is almost the same sweetness as regular sugar. So they could be probably swapped 1 for 1, not by volume probably, but by weight in a recipe. Glucose is less sweet, about 3/4 as sweet as sucrose. All the way down here to lactose. Look at lactose, 16. It's only 16% as sweet as sucrose. And this is interesting because milk actually contains a significant amount of sugar in it in the form of lactose. But when you drink milk, it doesn't taste especially sweet. And that's because the particular sugar that's in milk just isn't very sweet. Our tongues just have not evolved receptors that are very sensitive to lactose for whatever reason. I guess when you think about it, our tastes have evolved to cause us to prefer some food sources over others, if you think about it from an evolutionary perspective. And for us to eat lactose, the only time we would ever have lactose during our evolutionary times would have been as an infant. And in that, there's no food choice at that point in your life. You eat that and nothing else, where typically adults would not be eating milk products. I think actually most adults still are unable to digest lactose. The enzymes to break down lactose, which is lactase, in most humans disappear sometime in childhood. Although for European descended people, I believe it was, I don't know when, but sometime during our evolution, we sort of, we evolved to no longer lose that enzyme, or many people have. So many adults of European descent are able to still digest lactose, which is actually fantastic for survival in more northern climates because you can take things like milk and you can preserve them in the form of cheese, and you can then have easily stored high-fat, high-protein foods to survive in the winter when you can't easily go find food. So there we go. Very helpful. There's this other product here, HFCS 42%, and I'm going to talk about that in a minute. This is an engineered sweetener. It's not a naturally occurring thing. It's something that we produce, we make, as a replacement for sucrose because it's cheap and abundant. It's exactly the same sweetness as sucrose, and that's by design. This is engineered to be the exact same sweetness as sucrose, so they can be used as a one-to-one substitute. We'll talk about that in a bit. Notice fructose, though. Fructose is a sugar. It's simple sugar. It's the one with the 5 carbon ring. We are more sensitive to fructose than any of these other sugars. So our tongue is very strongly activated by fructose, which makes sense because fructose is the dominant sugar found in many fruits. So if you think about it again from an evolutionary perspective, fruits were probably the main source of sweet food, and so it would make sense that we evolved enzymes that are maximally sensitive to fructose. Now, different animals, of course, have different taste buds, and like I don't know, my cat, for example, has no preference at all for sweet food. I don't think cats typically eat sweet food. But I don't know what it is. They're certainly sensitive to something because, like, I had these cat treats, and he goes nuts over the cat treats. And they look and smell, to me, exactly the same as his regular cat food, which he doesn't care about at all. So I don't know what's in those, but cat crack. There's also naphthalactone is another molecule that really, for some reason, cats are really sensitive to. This is a compound that's found in catnip, which for human beings, I guess, doesn't do anything, but how does it spelled? N-E-P, I'm not sure if that's an A. Beta-lactone, something like that. Anyway, if you're curious, you can Google it. First question, which of the following sweeteners is sweetest? That would be fructose. How many simple sugar units, monosaccharides, are linked together to make a molecule of sucrose? And the answer is 2, and they are a glucose and a fructose. So natural sugars are great. You know, we can get them in foods. We can grow plants that are high in sugar, like sugar cane. You can press the juice out, dry off the water, crystallize out table sugar. But we actually eat a lot of sugar. Human beings today, in North America especially, eat way more sugar than any of our ancestors ever would have. And we've come up with some pretty ingenious ways of ensuring that we have a good supply as well of sugar. So one of these, and I alluded to it before, was the production of something called high fructose corn syrup. And what you start with here is cornstarch. And cornstarch, at least in North America, is much more easy to come by than any other source of sugar. Like, you can grow sugarcane very well in tropical climates, like in the Caribbean, but you can't grow it in Canada. Maybe you can under certain conditions, but certainly you can't scale up the production of sugar that way. For a while in Canada, we used to produce sugar by using sugar beets, and they'd produce sugar and you can collect it that way, but that's not very high yielding either. But corn is easy to grow. We're masters at growing corn. We can grow huge fields of it and collect it with a big combine. So we've got a lot of automated ways of scaling up corn production. And you can take the starch out of the corn, treat it with a compound called xylose isomerase. And what this does is it converts that starch, that complex starch, into a mixture of fructose, glucose, and a small amount of other sugars. And basically what you can do is take this cornstarch and leave it in there, and based on the conditions that you pick, in terms of temperature and time and so on, you can vary the amount of the fructose that's in there. So the more fructose that's in this eventual mixture, the more sweet it's going to be, because fructose is sweeter than glucose and the other sugars that compose this mix. So they stop at 42% so that the final product matches sucrose. So it's like a 1-for-1 mix. And it looks like this. We would just call this corn syrup. It's been around a long time. I remember as kids, it was a sad day when we had pancakes, and we never had maple syrup as kids, but we had the Aunt Jemima stuff, which has been recently renamed, I think. It's not Aunt Jemima's anymore. It's got a new name. And so what you do, something sweet was better than nothing, and so my mom always had corn syrup, and sometimes we put that on. I'd say that was worse than molasses. So like the hierarchy for things to put on pancakes, at the very top, maple syrup, then like the artificial maple syrup, whatever the new Aunt Jemima brand is. Then I guess molasses, and then down at the bottom here is this corn syrup. I don't know why, it's sweet, but it has like almost no other taste to it. I don't know why it's off-putting, but anyway, you can use it in food. A lot of soft drinks use high fructose corn syrup. There was a big switch sometime, I think it was in the 80s, where a lot of producers like Pepsi and Coke switched from cane sugar, which is sucrose, to high fructose corn syrup. And I saw a conspiracy theory, and I don't know if this is true or not, but that Coke, there's this infamous marketing moment in the 80s where they abandoned their recipe and they came out with this new product called New Coke, and everybody hated it. And they switched back to the original recipe, so they went back to original Coke. And I think even today, if you buy Coke, it says like original Coca-Cola on the bottle, because they don't want people thinking it's something different. But apparently when they did that, during the switch, they changed from sugar to high fructose corn syrup. And people thought the whole New Coke thing, that whole debacle, was actually planned to distract from the fact that they switched the sugars. Who knows? They call it high fructose, which is actually kind of a funny name because it's not really particularly high in fructose. It's 42% fructose, whereas sucrose is 50% fructose by weight. So it's less high fructose than actual table sugar is, chemically speaking, right? I mean, I guess sucrose is technically 0% fructose, but once it enters our body, the first thing that happens is enzymes split it in two and creates fructose. So yeah, in terms of the amount of fructose that you can find in high fructose corn syrup, it's 42% for high fructose corn syrup, 42. Honey is higher. Sucrose is exactly 50%. And there's another product called high fructose corn syrup 55, which would be like a more powerful sweetener you could use. Has more 55% fructose in it. And you can get these other sweeteners. Like this one is agave nectar. So often if you go to, I don't know, like health food stores and sort of more alternative markets and things like that, you'll find a whole lot of other sweeteners as well that are derived from other sources, which claim either have health claims associated with them maybe, or sometimes the claims are more social justice type claims, you know, like cruelty-free or fair trade or whatever. But just to show you, you know, like in terms of the fructose, many of those, like agave nectar, I think agave is a type of cactus. And so I don't know what part of the cactus, probably fruit, and they derive, well, I guess if it's nectar, that suggests it's coming out of flowers. I don't know, I would think you'd need an awful lot of flowers to get any significant amount. But you can see like fruit juice concentrate, apple juice concentrate. This is a common sweetener that you find in many foods, and it looks healthy because, oh, it came from apples, or it came from pears, or grapes, or whatever. But it's just basically a mixture of sucrose, or fructose and glucose, typically high concentrations of fructose because it's coming from a fruit. Jasmine never had maple syrup. Her mom always buys Aunt Jemima. Wow, you're about to have your mind blown. Get some maple syrup. It's really good on vanilla ice cream. All right, so there is some concern that's expressed regarding consumption of high fructose corn syrup, particularly when it comes to obesity, because the obesity rates in most developed countries are on the rise, particularly in the US, which is much higher. And I think even Mexico is worse off than the US in terms of obesity rates. Canada's high, but not as high as the US. And I don't know, maybe everyone's skinny in Europe. I don't know what's going on there. But what happened is people noticed that the obesity rates started to rise around the same time that high fructose corn syrup began to replace sucrose. And so people sort of like hatched this idea that, well, maybe it's high fructose corn syrup that somehow that mix, that sweetener, our bodies very efficiently process that and convert it to fat, more so than other types of sugar. And maybe the increased consumption of high fructose corn syrup relative to other sugars is what's actually responsible for the obesity epidemic, or at least a main contributor. Of course, there's lots of other reasons as well. So they published this particular data, which what they were showing was the obesity rate in the United States, which is this X, which you can see it grows starting about the mid-80s. It roughly doubles from the mid-80s to about the year 2000. This paper was published in 2004, by the way. It's a little bit old now. And looking at high fructose corn syrup, which is the diamonds, the consumption which was there. So it looks like, you know, the rise that we've seen since, I don't know, 1975, say, they're kind of correlated to each other. And so this paper wasn't claiming that one is causing the other, but they suggested this as a potential link to look further into. This is something that's, I think, under continuous observation. I think the evidence linking the increase in obesity to conversion from regular sugar to high fructose corn syrup, I think that's really weak at the moment. If you were to ask me what my thoughts on this were, probably what's more important than the types of sugars you are eating is the total amounts of sugars that you are eating, right? The total calories that you're taking in. There may be a slight difference between sweeteners higher in fructose or higher in something else. But I'd say the still most important critical factor is the total amounts that are being taken in. Now, of course, people are conscious of eating too much sugar, and as a result, that can not just cause you to gain weight, but it can cause other problems as well, like diabetes. So people have been exploring other ways of satisfying their craving for sweet food without taking in huge amounts of sugar. And this is where chemists come in. We have created artificial sweeteners. And what these are molecules which trick our taste buds into believing that it's sugar, so our brains register this response that there's sweet food in our mouth. However, the compound itself contains little or no calories, so it doesn't actually generate any energy or fat in our body. So these are a couple of examples. Aspartame, saccharin, sucralose are very common ones. This ability of these compounds to trick our taste buds is a little bit like what we already talked about with bisphenol A, tricking certain receptors in our body into thinking that it's actually estradiol. So this is a very common thing, is that we have all kinds of receptors in our body that are designed to sense specific molecules, and we can often fool those by putting similar looking molecules in. And this is how a lot of medicine works, is we take drugs which target specific receptors in the body, like beta blockers, I believe, are a type of drug used for something to do with the heart. Is it blood pressure? Is it, I'm not even sure. But it's designed to mimic certain molecules and then target certain receptors and then elicit some sort of biological response. So this is what these molecules are designed to do. Notice the similarity in structure between sucrose and sucralose. Basically what's happened is an OH has been replaced with a chlorine here. This OH is replaced with a chlorine here, and this OH is replaced with a chlorine here. Otherwise, it's the same molecule. So you can take sucrose, change just the structure just a little bit, and what that allows you to do is create a molecule that no longer is digested in the body for energy like sucrose is. The other thing that changing these groups from OHs to chlorine does is it makes the molecule, first of all, less water soluble, because there's fewer OHs on there. The other thing it does is it changes, once it gets into the receptor, how well it sticks. So when you have these receptors, you can think of it as the molecule kind of goes in, fits into the receptor, but it doesn't stay there forever. It comes back out, and it goes back in, and it comes back out. The response, the biological response to having that molecule in your body can be greatly increased or decreased if you have a molecule that sticks better to the receptor or sticks less well to the receptor. And so these molecules as well will also stick better to those taste receptors than sugar. And as a result, they register as being much sweeter than actual sugar. There's natural ones as well. This is a pretty complex molecule called stevia, which was actually illegal to be sold in Canada until the year 2012. This is a relatively recent new addition to the sweeteners. The reason is lab tests were done on this molecule and it was shown to be mutagenic. Mutagenic means it would cause you to generate mutated cells, which could be either carcinogenic or cause birth defects if you are pregnant. But they kind of reassessed it in 2012 and realized that although it may be mutagenic at high doses, at typical levels of consumption, it is generally recognized as safe. So it has a fairly low acceptable daily intake of 4 milligrams per kilogram of body weight, kilogram per day, which is about 10 times less than that of aspartame. So of the artificial sweeteners, it's actually a little ironic because many people will choose stevia over the others because it's the only artificial sweetener that's natural, that's on the market. And they believe because it's natural, it's therefore safer and a better option, where in fact, it's actually more dangerous than basically any of the other artificial sweeteners are out there, based on the scientific data and the measurements that have been taken on this compound. It's extracted from, I don't know, is it a stevia plant? It comes from leaves. And it looks like sugar, but it's much, much sweeter than sugar. You don't need very much to sweeten something. So these are the brand names you might be familiar with for some of these things. So Sweet and Low is one 0-calorie sweetener. This is saccharin. Splenda is sucralose. aspartame is equal, Truvia is one brand of stevia. I don't think stevia has just a single brand. Well, probably true with all of these. And which one you actually use does matter if you are cooking, because certain ones of these get destroyed in the cooking process. Like I believe aspartame doesn't survive baking. So if you try to replace sugar with aspartame, it's not going to work. You can see the ADI here is the acceptable daily intake. It's about 50 for aspartame. I believe it's 40 in Canada. I think the number is slightly different in Canada versus the US. Stevia is 4, sucralose and saccharin is 5. Now, although these have fairly low ADIs and have potential issues if you eat too much of this stuff, the fact of the matter is that these are far, far more sweet than regular table sugar. So if you look at sucrose and give it a value of 1, it turns out that aspartame is around 200 times sweeter than sugar. So what that means is to get the same sweetness as 1 gram of sugar, you need 1/200th of a gram of aspartame. So what that means is you just need a tiny amount of aspartame in something to make it taste as sweet as sugar. So the fact that it might be toxic at high doses becomes less relevant because you're never really going to get that really high dose because of the incredible sweetness. And this is really a main driving goal when people are trying to design these compounds, is the sweeter they become, the less concerned you need to be about their toxicity, because you can use lower and lower and lower doses in the final product. Stevia is roughly the same as aspartame. Very, very sweet, although it has a slightly different flavor. Some people say it almost has a metallic kind of aftertaste. I know aspartame doesn't taste exactly the same to me as table sugar. It kind of tastes more, it's weird for me to say this, but cold is the word I use. It kind of tastes cold, if that can be a thing. Anyway. Saccharin is around 500 times sweeter than sugar, and sucralose is around 700 times. So because all of these artificial sweeteners are so much more sweet, you can get away with using a lot less. This compound here is a compound called lugdaname, which is a synthetic compound. People were making many artificial sweeteners and testing them. And this one was found to be, if you look at the zeros here, 30 million times sweeter than sucrose. So this is an incredibly sweet compound, 30 million times. So what that means is you could use tiny, tiny, tiny fraction of this and cause something to be incredibly sweet. Now this is not something that you can actually buy. This, I don't know, for whatever reason, never got approved. Maybe that's too sweet. Maybe there's a problem, Imagine if you ate something with this and then your mouth tasted sweetness all day long. Like maybe it was permanent, I don't know. Like that could be bad too. For whatever reason, or maybe they just couldn't produce it, who knows. But there you go. So they can engineer molecules that are extreme in terms of their biological response. Aspartame, and this is going to bug me, it's HO, not OH, is how you would write that. You want to draw it where the oxygen is connected to the carbon there. The structure of aspartame really, it's got kind of 3 parts. It's got this part, which is used to be methanol. CH3OH was methanol. It's got the blue part, which was an amino acid, phenylalanine. And it's got the red part, which is another amino acid, aspartic acid. And this is about as close to natural as something gets. 2 amino acids. Amino acids are the main elements of proteins, the subunits of proteins, that when we eat these, they break down and our body recycles them and uses them to build muscle. So what happens in our body is when aspartame enters our stomach, we have enzymes that are very good. They're, what do we call them, peptidases, and pepsin is one example, that break amino acids up into the individual amino acids. So before this can do anything in our stomach, it's broken up into aspartic acid, phenylalanine, and methanol. Methanol is not something you want to have in high quantities. Methanol is naturally present in things like wine. But too much methanol can make you go blind. But tiny, tiny, tiny amounts of methanol are produced all the time in our body anyway, present in foods. Aspartic acid and phenylalanine are actually found in anything that contains protein. FDA says this is one of the most thoroughly tested and studied food additives the agency has ever approved. There's a long history of safe use. Yet, there's all kinds of articles warning against aspartame, in particular, more so than any of the other sweeteners, because aspartame is present or is produced in the greatest amounts. They say it's by far the most dangerous substance added to most foods today. Arguably, sugar is way more dangerous in the sense that constant intake of large amounts of sugar are known to create obesity, which creates a lot of other problems, and diabetes, which causes other health problems as well. Aspartame does not. 2013, the European Food Safety Authority re-evaluated aspartame, looked at all the studies up to that point. I'm not sure if one has been done since then, but basically they say it's basically agreeing with what they said before. From chronic toxicity studies, a no observed effect limit of 4,000 milligrams a kilogram body weight a day was identified. Divide that by 100 and you get your value of 40 milligrams per kilogram for your ADI. And they agree that it's still safe. So the best science up to this moment indicates that there's no problem with eating foods sweetened with aspartame up to your ADI. And beyond that, you're moving outside your factor of 100 margin of safety based on the NOAEL. So what that means is your 40 milligram per kilogram body weight per day. Remember that aspartame is extremely sweet. You can use just small amounts to cause something to be as sweet as something that's been sweetened with sugar. So it works out to hit your ADI, you would need to drink around 21 cans a day. Okay, so that's basically your allowable intake. If you are consuming more than 20 cans of aspartame a day, probably a good idea to back off a little bit. Okay, and maybe not even because of the aspartame, but that's a lot of pop. It's going to rot your teeth out pretty quick. I say rot your teeth out. Sugar rots your teeth out, but I think Pepsi does too. Does it? Because it's acidic. I don't know. It's a good question. I was actually very interested in this because I found myself last year drinking a lot of like bubbly, like carbonated water, and like a couple a day in the summer. And I was wondering, is carbonated water, which is acidic, is that bad for your teeth? And it turns out it's not. There's a paper that's out by the American Dental Association where they say they actually tested, I think, people who drank a whole lot of carbonated water versus regular water versus sweetened drinks. And the sweetened drinks, people had tons of cavities. The other two groups had very few, and they had about the same as each other. So there you go. It's all good. Natural News has this to say: what is aspartame? 5 surprising facts you never knew about this chemical sweetener. Every sweetener is a chemical sweetener, right? I guess maybe that's not true. You could have like electrodes in your brain that stimulate your brain and make you feel like you're tasting something sweet without putting anything in your body. Except electricity, I guess. I don't know. So what are these 5 things that they're talking about? Well, this is it. First one is aspartame is converted by the body into formaldehyde, a cancer-causing chemical. Yeah, that's true. Because I said it breaks down in your gut and produces a little bit of methanol. Methanol will actually react with oxidizers in the body, enzymes, to make CH2O, which is formaldehyde, but it makes it in tiny amounts, and we have naturally occurring in our cells tiny amounts already of formaldehyde. There's lots of biochemical reactions that produce formaldehyde in our body. So it is true that it does make formaldehyde in our stomachs and in our blood, but it's like an insignificant fraction of the naturally occurring formaldehyde that's already in there anyway, if you led a perfect diet. So certainly the amount of formaldehyde that is produced by having a diet with aspartame in it has never been linked with any negative side effects. I'm going to come back to this one. No, maybe I'll jump in. Aspartame causes obesity and metabolic syndrome. So this is something that you'll read in a lot of places, saying it causes obesity, which is the reverse of probably why most people use it. Obviously, if you're diabetic, you'd want to use it as well to make it easier to control your sugars. And metabolic syndrome, what does that even mean? Well, first of all, I guess I jumped the gun here a little bit. I'll come back to that. So when we say obesity and metabolic syndrome, I did some digging to try to find out where that claim actually came from. And I was able to trace it back to this paper that was published in Nature, if you remember, is one of our top 2 journals. And I found this pretty interesting. What was interesting about this paper actually was nothing to do about the dangers of artificial sweeteners. What it says is artificial sweeteners induce glucose intolerance transferable to germ-free mice. So what a germ-free mouse is they basically take a mouse and sterilize it. And I don't mean sterilize it so it can't reproduce. I mean sterilize it so there's no other microorganisms at all on the mouse or in the mouse. So basically they give it huge doses of antibiotics to clear out its GI tract. And so they're these kind of like sterile mice they have a collection of. Then what they did is they took other mice that they were able to give them giant doses of artificial sweeteners and cause a process called glucose intolerance in those other mice, those test mice. And glucose intolerance is believed to be a precursor to diabetes. This was done in the name of diabetes research. And what they're able to do is then cause this sort of disease state in these mice with these huge doses of artificial sweeteners. And then what they actually did is they took the feces of those glucose intolerant mice and they inserted it inside the GI tract of the sterile mice. And the sterile mice developed the same glucose intolerance symptoms as the original mice, despite never having come in contact with the artificial sweeteners. So what research is really showing is that glucose intolerance, at least in some cases, and potentially early onset diabetes, might be a consequence of our gut flora, what microorganisms are living in our gut, and not just a result of something else. So it was very interesting for that reason. What they actually did, though, is tested a number of different artificial sweeteners to induce this state in the mice. And the one that actually worked was saccharin. Aspartame didn't actually induce this state. But the time it got to Natural News, they had said aspartame causes obesity and metabolic syndrome. It's not aspartame, it's saccharin, and it's at like ridiculous doses that they specifically gave to induce that cause. Right? So this is kind of a bogus claim. Although it's funny, because it's not completely without truth. It's not like completely invented. It's just a small kernel of truth that was like really twisted, exaggerated to make a point, other than what the original authors were actually making. Just back to the first point again, formaldehyde we talked about. Formaldehyde is naturally in wine. A bottle of wine contains roughly the same amount of formaldehyde that you would get from the aspartame in 10 cans of pop, if you want an idea there. It's probably easier to drink a bottle of wine than 10 cans of pop. I'll say this too, if you drink a bottle of wine a day, probably the risk to your health is not the formaldehyde, it's the alcohol. That's what I find about a lot of these types of papers, and this is what kind of bugs me about them, is they try to get people afraid of these like minor compounds like sweeteners and preservatives and so on under the guise that they're unnatural. And what that does is I think it distracts people from the actual problems in their diets, which are high sugar, high processed carbohydrates like flour and so on, fat, salt, things like that. It's the big baddies, right, that everyone knows. But it's easy to say like, oh, I'm eating healthy because I'm pouring 4 tablespoons of honey in my coffee instead of sweet and low or something like that. It's not the way to think. These other ones, Reagan appointed FDA commissioner to help get aspartame approved despite evidence showing its toxicity. That's like back in the 1970s. This has been approved and retested many, many, many times. It's made from the feces of genetically modified GM E. coli bacteria. This is actually true. That's how they make aspartame now. They have genetically engineered E. coli to produce aspartame, and then they can produce the E. coli in big vats, and then they can extract out the aspartame and purify it and sell it. To call that feces, it's a bit disingenuous. Like E. coli are bacteria. They don't have GI tracts. They don't create feces like we create feces. In the same way, you could say yeast, like alcohol, you could say is the feces of yeast. I mean, I guess if you want to think about it that way, but it's using kind of gross out tactics. It's not really the case. If you don't like genetically modified things, well, that's a whole separate issue, which I think is separate from chemistry, but there you go. Aspartame crosses the blood-brain barrier, potentially causing permanent brain damage. Aspartame doesn't even cross your stomach-blood barrier. It doesn't get out of your stomach. It's broken down into those amino acids right away. If you injected aspartame, which I do not recommend, I guess maybe it could. I don't know. But I don't see how this could possibly end up in your bloodstream unless you injected it, which is definitely not a great idea. Yet, these types of articles gain traction. A lot of people read them. It's a very common belief about people who I know, friends of mine, that just aspartame, well, that's bad, right? It's a chemical. Of course it's bad, right? And so you see Diet Pepsi, now aspartame free. Why? Because there's fear out there. Pepsi is not in the business of standing behind the scientific veracity of their toxicity claims and all this sort of stuff. They just want to sell pop. And if people stop buying it because it's perceived to be aspartame free, then because it's perceived to have aspartame, then they'll switch it to something else, some other sweetener. So there you go. Aspartame is broken down in our gut to what substances? And the answer there is methanol and amino acids. 4, what artificial sweeteners was associated with glucose intolerance, which might be an early stage of diabetes? And the answer was saccharin. And that's, again, in the mice study at like ridiculously high doses. So whether that has any meaning for us is up for debate, I suppose. The next piece that we wanted to talk about was fats. And fats all have a very similar structure. They have this sort of 3-carbon chain at one end with then 3 molecules attached, which we call fatty acids. So if you take the molecule here in the middle, we call that glycerin, and then it forms what we call an ester with 3 different fatty acids to make these kind of relatively large molecules. And depending on what the fatty acid chains look like determines the type of fat it is, whether it's an animal fat or whether it's a vegetable oil or whatever. They all have that same general structure. We can do a reaction called saponification. And that's if we take a fat molecule, react it with 3 molecules of a strong base like sodium hydroxide, which is present in Drano, and you can break this up to bring back our glycerin, sometimes also called glycerol. I think glycerol is the chemical name, glycerin is a common name for it. And plus then you get these free fatty acid chains with sodium ions. That product is soap. So that's where we get soap from. It's from fats, treating it with bases. Now, fats can have these long chains which every kind of corner, every turning point in this chain is a carbon atom. And you can have chains with different lengths, different numbers of carbons. So palmitic acid, which is found in palm oil, is found in high amounts in palm oil, is that long of a chain. Lauric acid, I think, is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So any Lauras in the crowd, in the audience, your name means 12 carbons. Laura, lauric acid. Okay. The actual name for this comes from the laurel plant. And the laurel plant, I think in North America, is better known as the bay plant. So like bay leaves that you would put in soups. Those leaves are high naturally in fats that contain lauric acid, which is where the name comes from. Probably it was first extracted from bay leaves. Palmitic would come from palm oil. So when you have fatty acids where all of the bonds, all of the carbon-carbon bonds are single bonds, which is denoted by just these single lines, that means that this is what we would call a saturated fat. By saturated, when you think of a sponge as being saturated, it's full of water, it can't hold any more water. We would say these chains, which have hydrogens, 2 hydrogens on every one of these carbons, we would say the chain is saturated with hydrogen. You can't add any more hydrogens to the chain. Unsaturated fats, on the other hand, will have double bonds. So each double bond we could call maybe a unit of unsaturation. So you take something like oleic acid, which is a fatty acid that's found in olive oil in high amounts. It's got a double bond here, and we would say that this would make this an unsaturated fat, and if it just has one double bond, it's a monounsaturated fat. So monounsaturated, one double bond. Polyunsaturated means it's got 2 or more double bonds in it, in the chain. So linoleic acid is a common one that you find in, where's linoleic acid found? Anyway, certain plant oils definitely contain linoleic acid. So we would say this is a polyunsaturated fat or fatty acid. Another thing that we sometimes do is we label fats as being omega-3 fatty acids or omega-6 fatty acids. And the way we do this is we use the Greek lettering system to letter these chains. The first carbon next to the end group here, we call the alpha carbon. The next one is the beta, and so on. And the last one we call the omega carbon. Omega means end. And so what we do for fatty acids that are unsaturated is you go to the omega carbon and you count backwards until you get to the first double bond. So take the omega carbon, which is this one, go 1, 2, 3, 4, 5, 6. And on carbon 6, you start your first double bond. So we would call this one an omega-6 fatty acid, because the first double bond comes at carbon 6. 6 from the end. An omega-3 would have its first double bond at the third carbon in. So an omega-3 would have a double bond like between these two. 1, 2, 3, 5, 5, 6. That's brilliant. 4, 5, 6. Great. So oleic acid, by the way, whenever you have a double bond, like the one you see here, you could have a shape that looks like that, or you could have a shape that looks like that. This one that looks almost like a V shape, we call a cis double bond. This one that looks more like a line, we would call a trans bond. So double bonds can be cis or trans. In naturally occurring fatty acids, they're almost always cis. And what the cis does is it causes this chain to no longer be a straight chain anymore. It causes it to kink. And so what we notice is that saturated fats, like the ones over here, are basically like long lines, like logs. And what that means is if you have a lot of these fatty acids together and in making fat molecules, those molecules are these long kind of tubes that can easily stack up on top of each other, and they can pack very tightly together. And saturated fats, for that reason, are solids at room temperature because they can pack very nicely. So this would be what the case would be if you cook bacon and then you have all the bacon fat. You let it cool down to room temperature and it forms this solid white fat. Vegetable oils, on the other hand, are liquids at room temp. They're not solid, and that's because vegetable fats have a higher proportion of these double bonds. These kinks cause these chains to not lie flat anymore. Because they don't lie flat, they can't pack together as densely. They don't make solids, they make oils. So you can almost tell how much, whether it's saturated or unsaturated, by the degree of, whether it's liquid or solid at room temp. Great. This is just showing a bunch of different sources of fats and the percentage of saturated versus monounsaturated. You can see like safflower and canola oil have very low amounts of saturated fats, very high amounts of unsaturated fats, and they're all oils. Coconut, on the other hand, coconut oil is largely saturated fat, and coconut oil, if you leave it out at room temperature, becomes this white solid. You can see everything in between there too. Now again, us poor chemists can't leave anything alone. We like to do modifications of food if we can to make it have some property that's desirable, some or other property. It turns out it's a lot easier to get fats from vegetable sources than from plant sources because you can farm oil-producing plants at a large scale, where I guess with animals, I can't think of any animal that's farmed just for its fat. But anyway, there's a much bigger plentiful supply of vegetable oils and therefore a much bigger supply of unsaturated fatty acids for us to use to make foods out of. Problem with unsaturated fatty acids, while they're actually believed to be healthier for us by and large, that double bond is a site of reactivity. The double bonds make this molecule less stable and more prone to reaction. In particular, the reaction is oxidation, and when double bonds in fats oxidize, we say the fat goes rancid. So when food goes rancid, it's because oxidation of the double bonds. It's actually the sites adjacent to the double bonds in fatty acids. So if you're making a food that you want to put in a box and put on a shelf and sell in a grocery store, you don't want double bonds in your fats because that decreases the shelf life of your product. Makes your food likely to go off sooner because of oxidation. And so there's ways around that. One is to add antioxidants to your food. One of them is BHT. Another one is to add antioxidants to your food packaging. Seal them in bags, right, to keep air out. There's lots of things like that you can do to slow down that rancidity process. But a surefire way to do this is by doing a process called hydrogenation. What that does is it adds hydrogen to the double bonds and turns the double bond back into a single bond. It converts a saturated fat into an unsaturated fat. So unsaturated fats don't react, but they don't go rancid like these other unsaturated fatty acids will. They're far more stable, far more rugged. They last a long, long time. And so for that reason, these are highly desired by the food industry. So it's much more likely that processed foods are going to be higher in saturated fats than unsaturated fats. And you can tell yourself if you look at the packaging. If it says hydrogenated vegetable oil on the back, it's really not like vegetable oil anymore. It's like saturated fats at that point. Also, and this practice is becoming less common now, if you do what's called partial hydrogenation, which means you start the hydrogenation process to turn the double bonds into single bonds, but you stop partway, you can leave behind these other compounds which are unsaturated, but they still have these double bonds which are in the trans configuration. So we call this thing a trans fat. And trans fats are the worst of them all. They have the same structure and shape, relatively speaking, as a saturated fat, but our body doesn't recognize it as being a saturated fat, doesn't process it in exactly the same way. So partial hydrogenation is probably the worst type of fat that you can consume. Fully hydrogenated fats would be the same as just eating a saturated fat source like coconut oil. And that's that. So it's believed that a diet high in trans fats, and high means greater than 2 grams per day, which is very easy to reach if you're eating foods that contain trans fats. They pose health risks because they lower the levels of good cholesterol, raise the levels of bad cholesterol, which raises the risk of heart disease. In 2015, the US FDA determined that they are not generally recognized as safe and put in place a 3-year time limit for the removal from processed foods. Canada has weaker regulations on trans fat than this, but many food manufacturers, in response to health concerns around trans fats, have phased these out. Because what they basically used to do is take something that was like 100% unsaturated, partially hydrogenated to, I don't know, like 40% unsaturated, and that would leave behind all these trans fats. Now what they do is just take 40% of the 100, fully hydrogenate it, and then blend it with 60% unsaturated. So they make blends now which doesn't leave behind any of these trans fats. So it's actually a relatively easy problem to overcome. A little bit more work involved in the processing, but not that hard to do. Now, another reason actually why you'd want to hydrogenate things and why you might only want to partially hydrogenate them is because we know that oils convert to kind of soft creams to eventually a hard solid when you go from 100% unsaturated to 100% saturated. So to produce a product like margarine that is spreadable, that's soft, but also not a liquid, you want to hit the exact kind of ratio of saturated to unsaturated fatty acids. So that's why they only go a certain distance and then stop, because it allows you to make something like margarine. What process converts unsaturated fats to saturated fats? And that process is hydrogenation. Saponification turns it to soap. What type of fat is alpha linoleic acid? ALA. Is that the one I showed before? I don't think so, was it? Linoleic acid. Yeah, linoleic acid. This one's alpha linoleic acid, which is a different molecule. How do you find out? Well, it's obviously unsaturated. It's obviously polyunsaturated because there's 3 double bonds. You'd look at the last carbon and you'd count 1, 2, 3. This would be an omega-3. It's a double bond, 3 carbons in from the end. What types of fats pack together best to make solids at room temp? That would be saturated fats. So what's better for you, butter or margarine? This is the age-old question, and the advice on this actually has fluctuated back and forth a couple of times over the years. People used to use butter almost exclusively before we figured out we could make butter substitutes like margarine. And butter, because it comes from animal fat sources, is typically quite high in saturated fat. And we could have guessed that anyway because we know butter at room temperature is a solid. It's a soft solid, for sure, but definitely still a solid. So it's high in saturated fat. So when margarines came out, they were kind of sold as the health option because they contain less saturated fat and more unsaturated fat. And we know unsaturated fats are better for us in our diet than a diet high in saturated fat. And it's not that simple though, because margarine actually can come in different forms. You can get margarine that's soft margarine, which would be in a tub, like Baysal, and you can get margarine that's hard margarine that comes in sticks. And those are not the same thing, as we will see. So butter, if you look at its fat content, if you just buy a brick of butter and you look at the content in there, it has a lot of fat. It's got 8 grams of fat for 10 grams, so it's 80% fat. Got a little bit of water, a little bit of protein and other things in there as well. Tiny, tiny amount of protein. You can see that of that 8 grams, 5 of it is saturated, and 0.3 is trans fat. Where does that trans fat come from? Because butter isn't hydrogenated at all. And the answer is that dairy fats actually naturally contain small amounts of trans fats in them. If you concentrate that into butter, you're going to have a higher concentration than you would in something like milk. So butter, about 63% saturated, about 26% mono-unsaturated, and 4% or so trans fats. And so what you'd love to be able to do is maximize your unsaturated, minimize your trans, and minimize your saturated fats. So margarine, as I said, has 2 different kinds. The hard kind, and this is just one brand, Parquet, very common, hard one. And this label might be old. I think a lot of these in the last year or two have really changed their formulation. But you can tell right away for 9 grams here of fat in a tablespoon, you're going to get 1.5 grams of saturated, 1.5 grams of trans fat, which is a lot, considering 2 grams, higher than 2 grams is like a diet high in trans fat. And you get 1.5 grams just from a single tablespoon of this. Like a single tablespoon you could easily spread on a piece of bread. So 2 pieces of toast and you're 50% over. Polyunsaturated, monounsaturated. So it's sold as being healthy because it has this high amount of unsaturated fat, right? Together, these two give you 56%. So it's over half unsaturated with a small amount of saturated, but it's got a really high amount of trans fat, which is really bad. This is the stick margarine. This is the kind that you would buy in blocks and use typically as a substitute in baking. I ate a lot of this as a kid. Becel, though, on the other hand, the soft margarine, is very, very high. It's a lot softer than the stick margarine or butter. And as a result, it's got a higher amount of unsaturated fatty acids. Higher amount of unsaturated means it's more oil-like. And it's got no trans fat, which is great, and small amount of saturated fat. So if you were to ask me what I think is best, I would say the worst of the 3 is the block margarine. Butter is in the middle, and I would say tub margarine is probably most healthy of the 3. A funny thing, actually, butter, actually the quality of butter is, or at least used to be, and same with cheese, it used to be measured as a function of its color. So cheddar cheese is orange, and the highest quality cheese was the most orange cheese because the animals that produced the milk, the cows, would eat sort of grass and things in the field, and they would extract from their diets a chemical called beta-carotene, which is bright orange. That would end up in their milk, and that would end up in the cheese. So the better the diet of the animal, the more beta-carotene they would take in, the higher the quality of the milk, the more yellowish the milk was, the more the cheese was orange. So when we make cheese today, because cows eat like silage and hay and this sort of thing, and very low beta-carotene, the milk they produce is very white, and as a result, the cheese they produce is also very white. You know, think of like regular white cheddar. That's what all would look like. The stuff that is orange has been dyed orange, and guess what they use as a dye? Beta-carotene. It's the exact chemical that they would usually look for in high quality cheese is what they put in it to make it look orange as well. There's nothing wrong with that. They add that as well to butter, to like Becel, to make it look a little yellow, because natural butter is a little yellow. The more yellow it is, the higher the quality. So they can add a little beta-carotene to that as well to give it a bit of color. And I seem to remember seeing this before. The memory of this is foggy, but they used to sell this margarine in like, it was like white as snow, and that came with a little packet of dye, and you put the dye in and you'd mix it in to make it yellow, which, I don't know, the super white margarine just seems like really unappetizing for some reason. But really, it's got a dye in it that's not naturally in there anyway, so it's funny how we can be tricked to like certain things. Last thing, we have 6 minutes left. Olestra. Olestra is a fat substitute, which which I believe is not approved for use in Canada, but it is in the US. You can buy chips that instead of cooked in fat, fried in oil, they use this fake fat, which is called Olestra. And Olestra, if you look at the chemical structure, is quite ingenious. What the chemists who made this did is they took a molecule of sucrose and they added fatty acids all the OHs. So they basically took a triglyceride, which would be a normal fat, took the fatty acids off and stuck them on sucrose instead. So you get this molecule that looks an awful lot like fat, and if this broke apart in your body, it would just create fatty acids and sucrose, which are natural foods anyway. So it turns out this is a big enough molecule that our enzymes can't handle it, can't digest it. And so what this molecule does is passes right through our GI tract, comes out the other side. So this is problematic for a few reasons. One is the following. Olestra may cause abdominal cramping and loose stools. So it can cause gastric distress if you have any significant amount of this because you have a bunch of fat moving right through your body. I watched a YouTube video once. I was curious to see what the maximum number of calories you could consume in one day was. And this guy made a YouTube video where he drank 4 liters of vegetable oil and he didn't absorb all that. So anyway, if you're looking for a fun time, take a look at that. The other problem with Olestra is because it's non-polar, when this is part of your diet and it travels through your system, it kind of acts a bit like a sponge for anything else that's also non-polar. So you have lots of fat-soluble vitamins, non-polar vitamins, like vitamin E, vitamin A is another example, D, I guess, and K. Those, what will happen is they will sort of dissolve into this Olestra, this fake fat, and then that carries it right out your body on the other end. So actually, if you eat a lot of Olestra, it can prevent you from absorbing certain vitamins, fat-soluble vitamins that would ordinarily otherwise be in your diet. To make up for this, a lot of these products will actually load them up with supplemental vitamin A, D, E, and K, so that even though you might lose some, they're giving you more than would be present in the food anyway. Overall, though, I probably would not recommend Olestra from a maybe discomfort perspective. I don't think it's like chemically, it's not poisonous, it's not going to do anything bad to you, but it would have these problems that are indicated here on the label. You can't get them in Canada anyway, and you can't travel to the US anyway, so this won't be a problem in the near term for people. It's made by what 2 chemicals? It's made by combining sucrose and then regular old fatty acids. Great, so that's it for today. That's all we're going to cover. We're done this unit. It's a nice kind of chunk size unit, fits into one class section. And we'll meet again next Tuesday for 2 remaining classes. Don't forget, assignments are due later today. And good to see you all.